Last time, we had the discussion on the definition of an eigenvalue and eigenvector. For this lesson and this video, we are going to find an eigenvalue and an eigenvector for a given matrix. How do we find eigenvalues and eigenvector for a given matrix? The equation, the determinant of the quantity lambda times I minus A equivalent to 0 is the characteristic equation of the matrix A. Moreover, when expanded to the polynomial form, the polynomial, that is the expression resulting from the determinant of lambda times I minus A equal to 0 will be lambda raised to n plus c sub n minus 1 times lambda raised to n minus 1 plus plus c sub 2 times lambda square plus c sub 1 times lambda plus c0. This is the characteristic polynomial of A. So the eigenvalues of an n by n matrix A correspond to the roots of the characteristic polynomial of A when the determinant of lambda I minus A is equivalent to 0. Now, these are the steps in finding the eigenvalue and eigenvectors. Let A be an n by n matrix, that's a square matrix. First, form the characteristic equation, the determinant of lambda times I minus A equivalent to 0. It will be a polynomial equation of degree n in the variable lambda. Then, find the real roots of the characteristic equation. These are the eigenvalues of A. For each eigenvalue lambda, find the eigenvectors corresponding to lambda I by solving the homogeneous system of linear equation, wherein we have the lambda I times the identity matrix I minus A times X equivalent to 0. Now, this can require row reducing an n by n matrix. The reduced row echelon form must have at least one row of zeros. Example. In example number 5, we're given A, which is a upper triangular matrix, and we're asked to find the eigenvalue and corresponding eigenvector of this matrix A. Also, what is the dimension of the eigenspace of each eigenvalue? So again, looking at A, we will have an upper triangular matrix. So according to the step, we first need to form the characteristic equation, the quantity, or that's the determinant of the quantity lambda I minus A equal to 0. So doing that, we consider getting lambda multiplied by I minus A, which will result to this matrix. So we will have lambda minus 2, minus 1, 0, 0, lambda minus 2, 0, 0, 0, and lambda minus 2. And since we're asked to find the determinant, we can just apply the technique for a upper triangular matrix. Recall that the determinant of an upper triangular matrix, a diagonal matrix, is simply the product of the elements in the main diagonal. So we will have lambda minus 2 times lambda minus 2 times lambda minus 2, or we will have the cube of lambda minus 2, equating it to 0, we see that lambda is equivalent to 2. So next thing is to form the homogeneous linear equation, that is lambda I minus A multiplied to X equal to 0. So we do that, and replacing the value of lambda by the eigenvalue 2, we form the linear system, which is homogeneous equation. So we will have 2 times I, this is the identity matrix, minus A times X equal to 0. And we form row reduction operation. So we have here 2 times I minus A will be equivalent to this particular matrix, and we see that we will have 2 rows of zeros, which implies that X sub 2 is equal to 0, and we can consider x sub 1 as well as x sub 3 to be free variables, and so finding the solution to a homogeneous linear system in terms of a parametric solution using the parameters s for x sub 1 and t for x sub 3, we can conclude that the eigenvector of lambda equivalent to 2 are of the form. So we will have here x and its component x sub 1, x sub 2, x sub 3. And since we assign x sub 1 to be s and we know that x sub 2 is 0 and x sub 3 is equivalent to t, we end up with two vectors, that is the vector 1, 0, 0 and the vector 0, 0, 1. And since we have two linearly independent vectors, then the dimension of the eigenspace is equivalent to 2. Now, Theorem 7.3 tells us about the eigenvalue of a triangular matrix. If A is an n by n triangular matrix, then its eigenvalues are the entries in its main diagonal. Example, find the eigenvalues of each matrix. We have here matrix A, which is a lower triangular matrix. So this, according to the theorem, the entries in the main diagonal are the eigenvalues of the matrix. So here we will have lambda 1 equivalent to 2, lambda 2 equivalent to 1, and lambda 3 equivalent to -3, since we will have a lower triangular matrix. In letter B, we will have a diagonal matrix, and we can identify the following diagonal entries. And following the theorem, we can see that since this matrix is a 5 by 5 matrix, and so we will have 5 eigenvalues, namely lambda 1 to be -1, lambda 2 to be 2, lambda 3 to be equal to 0, lambda 4 equivalent to -4, and lambda 5 equivalent to 3. Now, without using Theorem 7.3, we will apply the concept that we can solve for the eigenvalue of a given matrix using the determinant of lambda times I minus A equivalent to 0, which leads us to a characteristic equation wherein the roots of the characteristic equation are the eigenvalues. So again, doing that, we will have the diagonal entries having lambda minus 2, lambda minus 1, lambda plus 3, and the rest of the elements with the sign opposite to the given matrix. And here, we will have the determinant to be lambda minus 2 times lambda minus 1 times lambda plus 3, and equating it to 0, we will have lambda 1 to be 2, lambda 2 to be 1, and lambda 3 to be -3, which is just exactly the same as when we apply Theorem 7.3. In letter B, we use Theorem 7.3 to conclude that the eigenvalues are the main diagonal entries. So we have identified it earlier for finding the eigenvalues and eigenvector for a given square matrix, and we only need to apply the determinant of lambda times I minus A equivalent to 0 to come up with the characteristic equation. Thank you for listening. In the next video, we will learn how to find a matrix that is similar to a given matrix A.